So let me prove this statement. The only thing to prove here is that two different expressions end up with the same rational number. So to prove that it cannot happen, namely two different expressions yield, after evaluation, two different rational numbers. So, for the sake of a contradiction, we assume that two numbers are the same, the evaluation given by expressions a1, ak, an is equal to a0, a1, ak prime, an prime. So with ak different from ak prime, and this is going to be the first discrepancy. Of course, the discrepancy may begin with a naught, then k is equal to 0. K is the index of the first discrepancy. Before that, they are all equal. After that, these are different. Something goes on. Possibly equal, possibly different, but these two are different. So, this inequality implies that implies that the two remainders are different, are key, is not equal to R prime k. That is because what is our remainder? R key, by definition, is a key semicolon a key plus 1 up to an, which is, when we evaluate everything, this is a key plus 1 or a key plus 1, plus 1 over, and so further. Now let us look at this thing. This is an integer. This thing all involves positive integers, adding fraction, flipping. Anyway, this is something positive. So positive integer plus a positive is bigger than 1. This is at least 1 positive integer. This is at least 1. They are all positive integers here and there, everywhere, by our definition. So this is at least 1. This is something positive. The sum is strictly bigger than 1, and flipped is strictly smaller than 1. So that whole thing is strictly smaller than 1. That implies that our key after evaluation is going to be in between a key plus 1 and a key, and similarly, by the same token, our key prime is going to be between a key prime and a key 1 plus 1 prime. These, this way will prove nothing. Integer plus something strictly smaller than 1. Which is going to be a key plus 1, a key prime plus 1. So these are two intervals of length 1 open integrals, and their left ends do not coincide. As a result, these two intervals of length 1 cannot overlap. They start at some integer, a key or a key prime, which are different, and go right exactly 1. There are no integers inside. All inequalities are strict. So this is either the same interval, but the left ends are not the same. So these are two distinct intervals of length 1 between integers both open. They do not overlap. That implies our key is different from our key prime. The intervals cannot overlap. From here, now in our key is different from our key prime, in its term implies that the previous remainders are also different. Well, that is because r key minus 1 is equal to a key minus 1 plus 1 over r key, while r key minus 1 prime is a key minus 1 plus 1 over r key prime. Remember, these were the first different terms. Before that, they are all the same. That was our assumption. Since they are all the same, a k minus 1 here and there is the same, while these two are different. So their sums are different. And now, induction argument allows us to repeat this step. So repeat this argument inductively. Until, so we go now from right to left in our evaluation of a finite continued fraction up. Until we get to the very first R key, which is R0. By the way, when key is 0, R0 is the expression itself. 0, semicolon, 1, and so further. So we recall, so until we get that R0 is different from R0 prime. And recall that R0 is A0 semicolon A1 up to AN, or put it this way, recall about what it was. A K A N, while R0 prime is A0 A1 up to AK prime up to AN prime. We have found that these two are different as we wanted. So the unpleasant thing does not show up. The correspondence is now one-to-one. We can go back and forth producing a continued fraction expression from a rational number or rational number from evaluation of a continued fraction expression. So we get a one-to-one correspondence. So if we do the same thing, not by rationals, but with real numbers, so that was theorem 1 in the text, which is not proved. Neither in the text nor in our discussion. I'm not going to prove this theorem. The proof is not beyond your ability to absorb it, but it is lengthy and full of technical details. I don't want to do that, really lengthy, but it allows one to produce a one-to-one correspondence. So there is one-to-one between real numbers back and forth and the set of now finite or infinite expressions, a naught, a one, last for finite expression if the expression is finite, then the last term is greater than 1. So we still need this same addition. Other than that, so we need to throw away some finite expression which got same produce same rational numbers as two of them produce the same rational number. Otherwise, this is a perfect one-to-one correspondence. That means that with continued fractions, we can construct the whole set of real numbers. That is another equivalent construction of real numbers. You possibly have heard about a construction with Dedekind cuts. That is going to be yet another one. I would better compare with a naive construction with Cauchy sequences. So that is Synonym remarks. That is similar to real numbers as infinite sequences of digits. we have sine plus and minus. After that, we have B0, B1, BS, decimal point, BS plus 1, BS plus 2, and so further. This sort of sequences of digits with decimal point. So here, in such a sequence, every digit is just a digit between 9 and 0. In our construction, I recall we have A0 instead of something like decimal point, we have semicolon, A1, A2, and so further. Now we have A0 integer exactly similar to this part together with the sign, and A1, AI for I from 1 and further, positive integers. So here, these are all digits. These are positive integers instead of digits. This construction is with continued fractions is in a sense much more natural. It does not depend on base 10 as this one does. This one we can do for any base. 10 is quite arbitrary, but they have chosen a base. Here we have not. No arbitrary choice was, we have to choose a base. Here, no arbitrary choice was made here. So from this perspective, the construction of real numbers with integers with continued fractions is a more natural one. No, it is not more convenient one. I still, if we want to construct real numbers, suggest to stick to the Dedekind cuts or Cauchy sequences. For many reasons, it may be simpler and more smoother to do. But still, it is smoother to do, but still, this is a vital alternative. The similarity is quite striking. So for in both cases, we have a glitch. So for decimals, like this, we have a glitch. Namely, you know, 1.000 is same thing as 0 and all 9. Two representations of the same rational number. For reals, we don't have, for reals which are not rationals, we don't have that. But for same rational number, we have two different representations. Now, for this construction, this one, we have a parallel glitch which we just discussed. 0, semicolon, 2 is the same thing as 0, semicolon, 1, 1. You can appreciate the parallelism. What we did, we have to exclude this one. We have to exclude this one. So we have to cross out this, and we have to cross out this to make the correspondence one to one. Another similarity, which is also kind of interesting, is we have rationals presented as you probably know pretty well by periodic sequences. Sequences which, from some point on, become periodic. These are rational numbers. Here, rationals among reals are presented as we have just proved by finite expressions containing fractions. Now I want to say that this is not exactly a parallelism because it forks. Okay, rationals can be easily characterized among decimal expressions and also among continued fraction expressions. However, these characterizations kind of different, periodic here and just finite there. You may say that finite is periodic from some point on all zeros. Yes, but not all periodic. What about other periodic expressions? Maybe they make sense, and that is indeed true. This is, again, not proved in this class. A theorem by Lagrange. Periodic continued fractions. Correspond to quadratic irrationalities. Those solutions of quadratic equations with integral coefficients, so roots. These are roots of equation ax squared plus by, bx plus c equals 0, a, b, c integers, and b squared minus 4ac positive. Otherwise, we don't have. So with continued fractions, there is no good way to go to complex numbers. So I'm speaking about only real quadratic irrationalities. For the sake of time and other constraints, again, this theorem is not going to be proved in class, and even this theorem is not going to be proved in this class. I just want to tell you something, but as I said in the very beginning, I want to tell you something about continued fractions, give an idea how some statements are proved. At the same time, I want to give you an idea about what kind of properties of the object you may expect. All right, I will thank you for listening. I will continue soon.